Hello everyone. Good evening, and great to see you. There's 10 of you so far. 11 now. Great. Okay, so can everybody hear me? Just type something in the chat if you can. Okay, perfect. Right, so today we continue talking about assignment 6, assignment 5, of course, and I'm going to do more questions on physics because I think well, it looks like physics is a bit more challenging as usual. Right, so I've prepared a few problems for you today. So let's have a look. And share screen. Okay. Right. So an object is stationary on a rough horizontal surface. A force F is applied to the object for delta t seconds. Well, it's a horizontal force, of course, a horizontal force. Horizontal force is applied for delta t seconds. Find the friction force if the object stops after 3 delta t seconds after beginning of motion. Okay, well, this is not a very difficult one. We are going to have a non-parallel force in problem 3, and this is way harder. So this is just to warm you up a bit. Okay, so horizontal surface, an object, a force F is applied. Okay. So there are different approaches to this problem, but I think the easiest one here is just to calculate the impulse. So the force F delivers an impulse. F delivers an impulse F delta t. F delta t. Find the friction force. So force F only acts for delta t seconds, but the friction force acts for 3 delta t seconds. So the friction force, the force of friction, friction delivers an impulse F friction 3 delta t. Okay, we've established because the friction acts all the way from start to finish, and the force F only acts for a time delta t. Okay, I'm just gonna rename this. It just looks a bit awkward. Force of friction times 3 delta t. Therefore, and because the object begins from standstill and ends with standstill, the total impulse delivered must be 0. Yeah, so the friction force. So this is not a difficult question in terms of math-wise, but it does show you an interesting concept. You can use this. So F delivers an impulse this, friction delivers an impulse this, and therefore we can write that F delta t is equal to force of friction 3 delta t, and the good mathematicians in you can obviously see that the force of friction is equal to 1/3 F, and that's the answer. So very simple, but an interesting way to do it. Yes, the impulse. So calculating the impulse delivered by forces. Okay. Right. Moving on. As a somewhat similar example, but in 2 dimensions. A spaceship has momentum p. It needs to change direction of motion by alpha degrees, keeping the magnitude of momentum the same. So without being less general about the problem doesn't become less general if we assume that the spaceship is traveling horizontally and a force, the engines will start working at this point. And as a result, the spaceship will change direction. So this has momentum p, and now it has momentum p, but in a different way. Well, let's call it p1 and p2. These are vectors. And the angle must be alpha degrees. So the question is, if the engines can produce a force F, for how long must be switched on? And secondly, in what direction should they be pointed at? And it seems like there are multiple solutions to this problem, because there are many different ways in which you can shoot the engines and change the direction. But the key thing here is that the momentum doesn't change. The modulus of the momentum the magnitude of the momentum stays the same. Therefore, you cannot fire the engine along the path of the projectile. So it has to be perpendicular. But if it's perpendicular, so assume we fire the engines that way. So the engines produce a force downwards. But almost immediately, this becomes like projectile motion. Yeah, in a way. You have a constant force acting downwards. So it will be accelerating downwards. And as it gains vertical speed, vertical velocity, it will start accelerating vertically. So the speed will be changing. So the force in some way has to always be perpendicular to the motion. So this is a bit awkward. So the force has to be always perpendicular to the direction of motion. Well, that's very easy to achieve, actually, if you think about it. You just put the rocket booster sideways and just fire. That's pretty self-explanatory. But let's see if we can produce find the average force. The average force. Okay, so we need some formulas, of course. So we'll start with writing as force times time is equal to the change in momentum. And of course, this is a vector, and this is a vector, and this is the vector of average force. Okay, we can rewrite this. The average force times delta t has to equal to P2 minus P1. And we will need a diagram for that. So P2 minus P1, if you remember how to subtract vectors, so this is P2 minus P1. This is P1. They have the same magnitude. P2, P1, and this is the value of P of F delta T. If you think about it, you can rewrite this as P2 is equal to P1 plus F delta T, the average force times delta T, which makes sense. Okay. Right. So from here, because this is alpha, okay, I haven't mentioned it by alpha, change direction of motion by alpha degrees. Alpha is small. Alpha is small. Okay. And from here, well, we can, because alpha is a small angle, we could actually say that this divided by this is alpha. Yeah, we can assume that this is a part of a circle. We can be more sorry. Okay, let's be a bit more anal and just calculate it. Okay, so F delta T using cosine rule, F delta T squared is equal to P1 squared plus P2 squared minus 2 P1 P2. And because we're taking the modulus P1 P2 times we're taking the modulus of this times cosine alpha. So this can be simplified as P squared plus P squared minus 2P squared cosine alpha, or 2P squared 1 minus cosine alpha. 1 minus cosine alpha. And therefore, F delta T is equal to P multiplied by square root of 2, 1 minus cosine alpha. Cosine alpha. So F delta T is equal to the initial momentum as momentum P, the momentum divided by, so F square root 2, 1 minus cosine alpha. Okay. Now, yeah, that works. So we can find delta T this way. We can use the small angle approximation here, and we can use the small angle approximation and find a much simpler version of this. Just a second. We know that if theta is small, then cosine theta cosine theta is approximately 1 minus theta squared over 2. And we can use this here. So delta t is approximately p square root 2, 1 minus 1 minus 1 minus 1 plus theta squared over 2, sorry, alpha squared over 2, of course, and divided by f, which is equal to, this is 0, 2 minus, oh, sorry, that's a multiplication. So 2 times, so it's alpha squared, square root of alpha squared. So it's going to be p alpha over f. And of course, alpha has to be in radians. Okay, p alpha over f. And finally, we need to find the direction of this, angle. So we know that this is a horizontal line. This is alpha. So this angle is, well, it's just using the properties of a triangle. So it's pi minus alpha over 2. Pi over 2 minus alpha over 2. Okay. Minus alpha over 2. That's the angle. Any questions? Oh yes, of course. You can use scalar product rearrange for alpha. So the delta t answer delta t is equal to p square root of 2 open bracket 1 minus cosine x cosine alpha bracket and divide by f. Direction. Well, let's do simple. Let's do in degrees. Direction is going to be one is going to be alpha over 2 to the vertical. Alpha over 2. Apologies. This is alpha over 2 to vertical. Vertical. Or you can simply say it's perpendicular to the direction of the ship. Well, the average force is this direction, but the force won't be changing. Or you could just use this force, which will also work. Oh, that is actually an interesting consequence. I haven't thought about it initially. You could point the rockets alpha over 2 to the vertical. What happens then? Well, actually, quite an interesting phenomenon. Because you're pointing the rockets this way, you're pointing the rockets, well, you're pointing the rockets the opposite way, but it's producing a thrust force this way. And this angle is alpha over 2. The rocket will start to slow down. The rocket will slow down and change direction as well. But from this point, from the apex, this force will the force is going to be, sorry, I shouldn't have drawn it like this. So this force so if this is the line, this is the line of symmetry of the path. first, the force, yeah, this is the line of symmetry of the path, and this is alpha over 2. This is alpha over 2. And because first, it will cause the spaceship to slow down because there's a horizontal component. But then it will cause the ship to accelerate because, so here we have a horizontal component which will slow the ship down, and here we'll have a component along the direction of the ship will cause it to speed up. So it will slow the ship down and then speed it up. Or you can constantly apply a force which is perpendicular to the direction of the ship, which would cause the ship to move in a circular path until it reaches that. Does that make sense? Does that make sense what I'm talking about here? Someone react, please. So yes, 1. Rocket shot 90 degrees to motion, and this will cause it to move in a circular path. Rocket constant speed, circular motion, and 2, rocket shot at a fixed angle, alpha over 2 to vertical. Here we have deceleration, followed by acceleration. Okay, I think that's enough for this question. It's not that a difficult question. It's just a few things I want to show you. Like I want to show you the approach, which is very important in physics problems. Right. Now this question, this is a very similar question. We have a very, very similar question in the assignment. It's one of the last questions. I don't remember which one. It's about a sandbag, but this is about a sandbox. So very similar. A box with sand, mass m, is on a rough horizontal table. Friction coefficient is mu. A bullet of mass m hits the box with speed v at an angle alpha. The bullet quickly stops in the sand. For how long will the sandbox continue to slide? And for what angle alpha will the box not move at all? What angle alpha will the box not move at all? Any ideas? Any ideas?
Yeah, I had an idea. So like for the bullet, I don't think we actually need to consider the vertical motion of it. So we can say that v cosine alpha, because we're interested in the horizontal motion.
V cosine alpha.
I was thinking about using conservation of momentum. So you could say that v cosine alpha multiplied by m, little m, which is the mass of the bullet.
Yep.
That's the initial momentum. And then we could say that that's equal to big M plus little m. And then the speed and that's in brackets, and then just you can make up a variable to say that's the speed of the sandbox after. Then you can rearrange to solve for what that variable is. And then I was thinking perhaps we could use f equals ma somehow to take into account that we've got the friction of coefficient mu to try and work out the deceleration. And we could do some suvat. That's what I thought.
M cosine alpha mv cosine alpha, yeah. mv cosine alpha divided by m plus m plus m. Yeah, that's the initial speed. And we can find the acceleration. What's the acceleration? What's the acceleration of the box as it moves? It's quite easy. The box starts to slide along the table. What's the acceleration? Because we know friction. We know friction is the only horizontal force that acts. No, not obvious. I mean, we've done this a few times. Okay, so I'm looking just at the box is sliding. So what happens in the box before is a bit complicated. So box is sliding. It's sliding, and there is the only horizontal force is friction. And we know that the friction force is mu r, sorry. And r is equal to that, mg is equal to that. Oh, sorry, it's going to be m plus m. It's going to be m plus m g. Okay, let's yeah, okay, m plus mg. So r has, yeah.
Isn't it like mu g? Because then you got like f equals ma. For
Brilliant.
f, we've got mu m plus m multiplied by g. And then for m, the ma part, we've got m plus m in brackets multiplied by a. The m plus m's cancel out and you get a equals mu g.
Absolutely. Sorry, m plus m plus m. You have the second Newton's law. So for mass times acceleration is equal to the total force, and the only force is mu m plus mg. M plus m cancels out, and you have acceleration. So whenever something is sliding along the floor, the acceleration is minus mu g. Please remember this result because this is very useful. So we have the acceleration, which is minus mu g, and we can find the time. We can find the time from v equals u plus at. We can find the time. So v is 0. Final velocity is 0. U is that monster. So that minus mu gt. From here we get t is equal to this divided by mu g. Okay. Now, if that was the case, this question would not have a star next to it, and this question would be a reasonably easy question. But it's not. This is an incorrect solution, unfortunately. Incorrect solution. Because what it does not take into account is that when the bullet hits the sand, it applies a force, a downwards force on the box. And this increases the normal reaction force. And as a result, it increases the momentum. Oh, sorry, increases the friction force. Okay. So when the bullet hits the sand, it exerts a downwards force. Its force on the sand. This increases the normal reaction force. The normal force on the table and friction, increases friction. This is friction. It's probably the hardest problem of today and the hardest problem of the set. Increases friction. So what happens is that we need to consider the impulse delivered. So what are the forces acting on the box? Now, so there is the mg, of course. mg, and there's the friction force, mu n, and there is the normal reaction force here, and there's the force of the bullet. There's the force of the bullet which acts this way, force. And this could be quite a significant force, of course. We split the force into components. And this is going to be F cosine alpha, F sine alpha. Now, impulse delivered by F is equal to, so the impulse is force multiplied by delta time, by delta t. And of course, it's equal to change in momentum, so it's equal to mv. Okay, so the horizontal impulse well, no, that's fine. So from here, we can write that the force is equal to mv divided by delta t. mv divided by delta t, that's the impulse. So delta t is the time in which the bullet stops. Delta t, the time it takes the bullet to stop. Now, impulse delivered. So we have a box of mass m, and we have an impulse delivered. Now, impulse delivered by the friction force, impulse by friction force is equal to mu n, because that's the friction force, multiplied by delta t. Delta t. Well, minus technically, of course, because it's slowing the box down. Impulse delivered by friction force is that. Therefore, so where are my notes? And then we can write for the vertical forces, we can write that the normal reaction is equal to mg plus f sine theta, alpha, f sine alpha. And we can substitute that in. We can substitute to the impulse from friction is equal to minus mu mg plus f sine alpha times delta t. Delta t Okay, let's continue. Let's carry on. So that's equal to minus mu mg delta t. Now F is equal to mv divided by delta t. So that's going to be mv sine alpha delta t divided by delta t. So it simply is going to be plus mv sine alpha. mv sine alpha. And here we need to really think like physicists. We need to understand that because the delta t is very small compared to the time it takes for the thing to stop, this value is negligible. We can neglect this value because mg delta t, well, that's the change of the momentum of the box during the very short collision caused by the friction force. And this is going to be a very small value. Caused by the normal friction force because of the box's weight, caused by the box weight, because the main friction force is coming from the collision. Yeah, the collision is a dynamic force. So when you hit, well, I mean, if I punch my hand, I don't really consider the mass of my fist. I don't really consider the weight of my fist. Yeah, if you think about it. So basically, what's going on here? So I have a book. Yes, the book is responsible for some of your problems on maths. So when I hit the book, it's a dynamic force. I don't need to calculate the weight of my fist. I need mv. Does that make sense? Okay. So when I hit the book, when I hit the book, of course, there's going to be two forces. The force is one force, the dynamic force, which is going to be mv, that's the mass of my fist times the speed of my fist divided by delta t. That's one force. And there's going to be another force, which is the weight of my fist, which is negligible, which is very, very small. So here, this value is very, very small compared to this because delta t is small. Right. So what we can write is the final momentum of the box after the bullet has stopped. So momentum of the box is going to be equal to the momentum, to the impulse delivered by impulse delivered by bullet minus impulse delivered by friction. And the impulse delivered by the bullet is going to be F. Of course, we're taking the horizontal momentum. Yeah, we're not considering the vertical momentum. Box X, horizontal momentum. So it's going to be F cos alpha delta t minus mu mv sine alpha. And F cosine alpha delta t can be written as mv cos alpha minus mu mv sine alpha. Okay, that is the initial impulse of the box. And now the friction force is going to kick in now. So once it is moving, once the box is moving, friction will deliver an impulse to stop the box. So we can write that the force of friction times delta t. Now this is a new delta t is equal to the change in, well, it's equal to this. And the force of friction is mu m plus m. Now we're using the result of the previous answer. M plus m g delta t is equal to that. And the answer, delta t, is that divided by ta-da. This is the time for which the box will slide along the table. So let's compare it to what we had previously. Well, if you look at it, the only thing that is new here, it's a very similar answer. But as I said, this the first answer does not take into account the dynamic forces. This does. So this predicts the box will move always. But this this predicts the time. Now then the second part of the question was, for what angle will the box not move at all? The box not move at all. Well, that means delta t is 0. Simply put, this means that this value is 0. If the box remains stationary, then this has to equal to 0. Equal to 0. Therefore, this bit has to equal to 0. Equal to 0. And from here, we cancel out MV. We get cosine alpha. Okay, I won't skip. Okay, I have to skip. It's going to go cosine alpha minus mu sine alpha. Divide both sides by oh yeah, divide both sides by sine alpha. Oh, actually, you know what? Divide by tan alpha. Okay, so I actually made a mistake. Not here. I made a mistake when I was preparing. And minus mu sine alpha equals 0. And equal that. So then tan alpha is equal to is equal to 1 over mu. 1 over mu, and alpha. Well, alpha has to be greater or equal to arctan tan 1 over mu. If alpha is going to be greater than that, then the box won't move at all. Okay. Right. How do you guys understand this problem? How is it for you on a scale of 0 to 10? It's a very difficult one. Scale of 0 to 10. Please vote in the chat. Okay. Good. But it comes down to those things. It comes down to the forces. Embarrassing. Okay. Problem 4. Another problem about containers with water. A glass container of negligible mass is on an absolutely smooth table, like unreal smooth. The container is filled with liquid of density rho 0 and volume V0. A beetle of volume V and density rho starts to crawl along the bottom with speed u. Find the speed of the container. Okay, so the beetle is the beetle has to have greater density than the liquid, of course. That's the first thing that should pop into your head. Okay, so rho has to be greater than rho 0. Otherwise, there couldn't be any friction between the beetle and the bottom, and the bottom of the container. And because of that friction, the beetle moves forward, and the container moves backwards. Now, you might have guessed that this is a center of mass problem. So let's say the beetle, the center of mass of the liquid is here. The center of mass of the beetle is here. We'll call this x1, the position of the center of mass of the liquid, and x2 is the center of mass of the beetle. Now, this might seem very, very tricky, because what happens is that the liquid has a cavity in it, and this cavity is at position x2. So it's going to be very difficult to find the center of mass of such a system if you just consider it separately, because not only you have to take into account the mass of the beetle, but you also have to take into account the you also have to take into account the cavity caused by the beetle. Okay, but I'm going to do it. I'm gonna use a slightly different approach here. I'm gonna say, okay, if the beetle had the same density as the liquid, no matter where the beetle is, the position of the center of mass wouldn't change. The distribution of mass would not change. Well, nothing would change. The beetle would be just like water. So I'm gonna assume, I'm gonna ask myself, what would happen if the other liquid had 0 density? Well, we are only interested in the mass of the beetle then. And if it has a density, and the beetle has more density, we can stick to the extra mass added by the beetle. So the extra mass, basically we're asking how much more mass is the beetle compared to when it's just liquid. Okay? The extra mass of the beetle is how much more mass how much more mass of it, how much the mass of it is more than the same volume of liquid. And the answer is very simple. How much the mass of it is more than the same volume of liquid. And the answer is the extra mass is rho minus rho 0 times the volume of the beetle. So this is the mass of the beetle compared to if the beetle was not there. Does that make sense? If it doesn't, please let me know. This is how we can take that into account. And therefore, we can simply write that the mass of the extra mass of water of liquid is rho 0 V0 ooh. I see. So there's a slight complication. It's not that great. V0 plus V. Yeah, we kind of need to take that into account because we've said instead of a beetle, we have the same amount of liquid plus the liquid. So the mass of liquid is going to be rho 0, which is the density of the liquid, times the volume of the liquid plus the volume of the beetle. So we assume that the beetle is filled. So there's a beetle-sized cavity which is filled with liquid. Okay. Have I lost anyone yet? Is anyone completely lost? How well do you understand so far? Please vote. Vote. Okay, that's good to know. So we find the center of mass. We know the position of the center of mass. Why is it doing that? The x center of mass is equal to a fraction m1 plus m2, and here it's going to be m1 x1 plus m2 x2. And then I remember a simple fact that without doing any calculations here, I'm just going to differentiate both sides with respect to t. Differentiating with respect to t. And we get the derivative of x is the velocity. So it's the velocity of the center of mass. So mass, because the derivative of x is, yeah, I'll just write it down that dx dt is velocity. And we get m1 v1 plus m2 v2 divided by m1 plus m2. And we know that the center of mass cannot move because there are no external forces. Therefore, this velocity has to be 0. So m1 v1 plus m2 v2 is equal to 0. And all we need is to substitute. So we substitute the extra mass. First we do the liquid, the mass of liquid. One is liquid, so it's this. Times the mass times V1 plus M2, which is the extra mass, plus this multiplied by V2. But beta, this velocity of the beta is given as u. The velocity of the beta is u. Speed u. Okay, we need to specify relative to the container. Because it's moving relative to the container is moving backwards with a speed v1. And so this is going to be not u, this is going to be u minus v1. And for clarity, because we're going to have many mistakes here if we get minus. We do minus because obviously it's moving backwards. Okay, the container is moving backwards. Therefore, we can use that fact. And this has to equal to 0. So we expand to find v1. Wow, that's a lot of things. Okay. VU minus this times V1 V1 equals 0, and V1 is equal to fraction. So it's going to be this. V1 is equal to this divided by, well, this plus this. Plus this. So from here, V1 is equal to that. Row 0 V cancel out. Row 0 V cancel out. So we get row 0 V 0. Row 0 V plus rho v plus rho v. UV rho minus rho 0, rho v plus rho 0 v. Aha, interesting. An interesting thing is that if let's say instead of a beetle there was some sort of I don't know, some sort of Spider-Man basically that can stick itself to the bottom. Imagine that, yeah. So imagine the beetle was lighter than water. Imagine the beetle is lighter than water, and that means that rho is less than rho 0. And the beetle had some way of sticking to the bottom and holding up. Oh, maybe there was a tiny ladder for a beetle. That means that this term is going to be negative. That means V1 is going to be less than 0. So the tank will move forward. So imagine the beetle crawling forward and the tank crawling forward, the tank moving forward. That's the significance of this. So, and that kind of makes perfect sense. If you think about a helium balloon in an accelerating car, imagine a balloon filled with helium and the car is accelerating. Normally, things tend to be pushed towards the back of the car in an accelerating car, but a helium balloon would actually move forward. This is a similar situation because the beetle is lighter than the water surrounding it. Moving it to the right will cause the tank to shift forward as well. Okay. Now, look, problem 5 is quite straightforward. It's just a conservation of momentum. It's just we have little time to discuss it. But basically, this is a math question, effectively. Sorry, it's obviously it's a physics question, but it's just math. So you just need to find the speed of the nucleus before decay. So we have a nucleus splits into 3 parts, traveling with momentum P1, V1, P1, P2, P3. And because they are mutually perpendicular velocities, find the speeds of the nucleus before decay. So what happens is there's a nucleus which is traveling, and then it splits into 3 parts. And they are mutually perpendicular. That means that they're 90 degrees to each other. So something like this. Yeah. Like this, mutually perpendicular, that's what it means. And you just need to do the maths. So we have M1 V1, M2 V2, and M3 V3. And these are vectors. So M1 plus M2 plus M3, M1 plus M2 plus M3, that's before the collision, times U, times the initial speed, is equal to M1 V1 these are vectors, and that's why I chose this problem, because these are vectors. But it's not very challenging. It's not a very challenging problem. All you need to do is to realize that because they're perpendicular, you can use the Pythagoras theorem. So the answer would be U is equal to the square root of m1 squared v1 squared plus m2 squared v2 squared plus m3 squared v3 squared, and all over m1 plus m2 plus m3. So this is the answer. I don't have much time to explain how I got there, but hopefully you understand. Now, this is a theoretical question. This is no. So imagine a horizontal treadmill with no friction on the rollers or axles. So what's that? What does that mean? Well, we have the two rollers on either side, and it's not powered. I forgot to mention that, but it's not powered. Of course, it's not powered because it can't be powered, because if there's no friction, there's no way to power it. Okay. Now, a person is on a treadmill and attempts to run forward. I mean, even if the belt starts moving, the mass of the belt, this mass of the belt is backwards, is moving backwards. So this belt has momentum mv, and this belt has momentum mv as well, but forwards. So the total momentum of the belt is 0. The total momentum of the rollers is also 0 because they're not moving anywhere, or the total momentum is 0. Right. Total momentum of tread and rollers is 0. That means that if the person is if the person is attempting to run forward, that means that there's no way they can run forward. Or does it? Or does it? So basically, my question is, can the person move forward in that situation? Because we know that the total momentum of the system, the total momentum of the rollers and the belt is 0. Does that mean that the total momentum of the person, is going to be 0? Anyone? Thoughts? Yes, they start standing still. The treadmill is not moving. The person is standing still, and the person tries to run forward. Will the person be able to run forwards, or it's just the treadmill is going to spin and the person is going to stand still? Like, is it possible to run forward? And of course, there is friction between the feet of the person and the treadmill. So they are. I hope that's clear. No ideas, no thoughts. You can use the microphone if you have something to say. What is your intuition? Yeah.
Right. So we know that the mass of the rollers is obviously going to be less than the person. So imagine if the person pushes back hard enough and jumps up at the same time. So then the rollers will go back faster than the person will move forward because of conservation of momentum. And then as soon as the person lands back onto the rollers, if the person starts running even faster, then they could start moving again forwards. You see what I mean?
Sorry, so the person pushes back, and because the mass of the rollers is less than the mass of the person, the rollers move back with a faster speed than the person.
Yeah.
Okay, fair enough.
And then the person will move forwards. And then as soon as the person lands back on the ground, if the person pushes back even harder, so to make up the fact that the roller's going back faster than they were moving forward, then they could move forward a bit more. Right. The momentum's always going to be zero, no matter what you do. But if you make the rollers go back really, really, really fast, then the person has to go forward.
The conservation of momentum doesn't stop working when the person goes really, really, really fast. So it would. So basically, if the person is able to walk to the front end of this thing, if the person is able to walk here and jump off, that means that that would effectively mean that the momentum of the system is not conserved. Because you start with zero momentum. You start with zero momentum. The person has zero momentum. The rollers have zero momentum. The treadmill has zero momentum. So what's going on? Why is the momentum not conserved? Or, I mean, if they are able to jump off, that means the momentum is not conserved. And if they are able to, if they are able to jump off, then it means momentum is not conserved. And if they if they can only stand still, that means momentum is conserved. What question do we need to ask ourselves when we consider conservation of momentum? When is momentum conserved? Okay, a very simple. This is a very simple question. When is momentum conserved? Well, you know the answer to that question. Yeah, no external forces. So are there any external forces? Well, it's difficult to see the external forces. It's very difficult to see the external forces for the whole system. I'll show you where they are. So momentum is not going to be conserved because there are external forces. And if we just look at the person, well, it becomes very obvious. There is a friction force pushing the person forward because the person pushes against the ground. That means that there is a friction force on the person moving forward. So the person is allowed to move, and that's the simple answer. Yes, the person can move because there's a friction force, and that's the only horizontal force acting on the person. So yes, the person can change momentum. Now, of course, there's an equal and opposite force on the treadmill. So how does that work? Well, actually, what's happening here is that these axles, when the person is pushing back, the whole system attempts to shift backwards, and that causes a reaction force, a normal reaction force, to appear in the axles, which actually push the treadmill forward. But the person pushes the treadmill backwards with an equal but opposite force, so the treadmill stays the same. So if you look at the treadmill will stay the same, stay still, because the forces are balanced. So this force and this force is balanced with the force of the human. The human is pushing back. And of course, in the axles, okay, I'm going to have triangular axles here. But for the person, the forces are not balanced and the person will jump off. So short answer, momentum is not conserved because there are two external forces and they are hiding here. They are hiding here in the rollers. This is the axle of the roller pushing the system forward. Okay, hope that makes sense. Okay, very quick one, but a very interesting one. I was just very enthused when I saw this question. You have n ping pong balls, each of mass m, bouncing on top of an electronic balance. There's no air resistance, and the bounces are perfectly elastic. What is the average reading on the scale? What is the reading on the scale if the bounce is not perfectly elastic? That's the second part of the question. Sorry. Okay. So let's consider one ball. They do not specify the height of the jump, interestingly, and they do not specify. Yeah. So let's start with one ball. Let's start with one ball, and it's bouncing. And for simplicity, I'm just going to use 5 meters. Why 5 meters? Can somebody guess why I decided to choose 5 meters as my initial height? How long will it take it to fall? How long will it take the ball to fall onto the ground, onto the balance? It takes 1 second. Yeah. From a height of 5 meters, the fall is 1 second. Another useful thing for estimations. For 5 meters, so the ball will hit the balance every 2 seconds. Every 2 seconds, the ball will hit the balance every 2 seconds. Every 2 seconds. The speed at collision, you can use SUVAT. The speed at collision. Can somebody do a quick SUVAT and calculate the speed? Okay, it's going to be 10. I really hope you're very familiar with the SUVAT, so I don't have to explain why this is going to be 10 meters per second. And also you can use conservation of energy, yeah, to calculate 10 meters per second. Meters per second. Then the impulse for one collision. the change in momentum is equal to 2mv, which is equal to 20 times m. And finally, impulse for one collision, and then the force is equal to the change in momentum, or the impulse change in momentum, delta p divided by delta t. Delta p divided by delta t. Delta t. And that's equal to 2mv divided by 2 seconds. Sorry, 2mv, so 20m. 20m divided by 2, which is 10m. 10m, which looks peculiarly like mg. So is that equal to mg? Is that the average force of one ball on the scale if it's bouncing? Is mg, which looks promising, because I think we might have just solved the problem. But let's this is a test for one ball. So let's test with a greater height. With a greater height, with a different height. Consider a ball falling from a height h. So we have mgh is equal to 1/2 mv squared, and v is equal to square root of 2gh. Or you can use Suvat. You can use Suvat and get the same result. 2gh. So the change in momentum delta p is equal to, for one bounce, the change in momentum is 2mv. So it's 2m square root 2gh. Looks good so far. Now the time to fall is equal to, well, that's an interesting one. You do need to use a Suvat here. So SUVAT. So S is H, U is 0, V is, we don't care, do we? Yeah, we don't really care about V. A is minus G. And, well, no, sorry, it's G. We can use G, and T is question mark. Okay, so we can use S equals UT plus 1/2 GT squared. GT squared. So so H 2H, sorry, H is equal to 0 plus 1/2 GT squared. So T is equal to square root. I'm ignoring the negative version, of course, because, well, okay, it's plus minus 2h divided by g, 2h over g. So time to fall is this. T is equal to SQRT of 2h over g, and time between two bounces is 2 times square root of 2h divided by g. You probably can see how much fun I'm having with this question. And finally, we get time between bounces. So we get the force of one ball on the scales when it's bouncing, the average force. The average force is delta P divided by delta T. Delta T, which is, this is delta T. So fraction is going to be that divided by that, and some 2h cancels out, g becomes g, 2 cancels out, and we have mg. Yay. So the average force of one ball is mg. And so the average force is mg. So for n balls, it's going to be nmg. For n balls bouncing is equal to nmg. So if you have ping pong balls bouncing on a scale, the reading would be, the average reading would be the same as if it was stationary on the scale. And I find this fascinating because it doesn't matter how high the ball bounces, because if the ball bounces from only 10 centimeters, that means that it will bounce more often with a smaller force. And if it bounces from a greater height, it bounces less often, but it hits harder. So the average force remains constant. And yeah, as a homework, I'll leave it to you to prove that if the collision is not elastic, the picture does not change. If the collision is not elastic, it's still nmg. It doesn't matter. So I'll leave it to you. Okay, so I hope that was useful, somewhat, and I'll see you. I'll see you next week. You're welcome.